Hi, yet another important video from the course Control Systems, Lag Networks. Some basic information regarding lag network. You may have a question. Draw the electrical lag network and derive the expression for the transfer function. It may be sinusoidal transfer function or the transfer function in pole zero form, etc. A little bit information regarding lag compensator. All right, how the network looks like, guys. This one we have a resistor, and another resistor and a capacitor. Giving the names, it will be R1, R2 and C, and probably this will be the input and this will be the output. And making use of the potential divider rule. What does potential divider rule says? Two resistors, n number of resistors. If we have R1, R2 plus VCC being the supply, the voltage across R2, V2, how to write down that? V2, which is equal to supply VCC into that resistance by total resistance, isn't it? So this would be making use of the same thing, whereas we have a resistor and capacitor in series. That's it. All right, so how to write the expression for V0? V0 will be equal to supply V in, and what impedance? The series combination of R2 and C. All right, the series combination of R2 and C, that's into, it's R2 plus 1 by j omega C, j omega S, so S into C. All right, a little bigger, S into C upon the total resistance, this one, I mean total impedance. All right, so it's R1 plus R2 plus this one, XC, 1 by j omega C, which is equal to 1 upon SC, j omega SC. All right, so from here itself we get the expression for the gain, isn't it? So this one Vi this side upon Vi. Now this will be the transfer function. What is that transfer function? What is that ratio in control systems? It's the ratio between output to input, isn't it? So output voltage, input voltage, this will be the transfer function. All right, and so here we have upon 1 over here, upon 1 over here, simplifying this one. Now G transfer function, G of S, GC compensator, they say, isn't it? To provide the compensation. What do we do with the compensations? We introduce a zero and a pole externally without disturbing the position of the existing uncompensated poles and zeros by properly selecting the values of new gain, crossover frequency, etc., something like that. Let's see what happens. That could be understood in the designing part. And as far as here, like in this video, I would like to furnish some basic requirements in order to design a lag compensator. All right, so here, and this one, as you know, like the LCM of this one will be SC, and cross multiplying this one will have 1 upon 1 plus overall, okay, 1 plus multiplying this one S R2 into C. Don't forget this one, okay, R2 into C combination, the product. In the same way, this one, the LCM will be SC, and cross multiplying this 1 plus S R1 plus R2 into C. All right, so we don't have this anymore. Upon SC, we don't have that anymore. All right, this gets cancelled over here, this gets cancelled over here. All right, so a little bit even more simplification over here, taking R2 as common from this and this. All right, so how to write down that one? GC of S, that will be equal to, take out R2 from here and here, take out R2 into C. So what is left over here? It's a S plus 1 upon R2 into C. All right, what about the denominator part? But take out this completely, this we need only S, okay, to transform this equation to pole zero form. S plus something, isn't it? In the denominator it will be pole, in the numerator it will be 0. So R1 plus R2 into C as common from this and this. So in the bracket we have S plus 1 upon R1 plus R2 into C. All right, so hope you understood the transformation. This isn't a big deal. See what next. So this one, Can this R2, yeah, something gets cancelled over here, this C and this C gets cancelled, all right. And can this R2 be written over here by R2? Will that be any problem? It flips, isn't it? And it will go back to its original position, isn't it? And this is C, all right. So here assuming R1 plus R2 by R2, which is equal to give some name like standard notation. Let this ratio R1 plus R2 by R2, let that be beta, all right. And another simplification is R2 into C, let it be R into C time constant T, all right. So making this transformations and plugging in over there in that expression, what do we have? See, where do we have that beta? Over here, 1 by, this is completely beta, isn't it? Now this one, this is now R1 plus R2 by R2, it's completely beta, all right. And this is T, all right. And even here we have a hidden beta and a T. Let this C be a bit far away from here, all right. Even here we have a hidden beta and a T. How is that done? So what if we do, will that be any change? Let this R2 be, all right, all right. So by R2 into R2, will there be any problem? Does this change the characteristic? This gets cancelled and we have the original equation, isn't it? Now here this part, this is the beta and this product will be the T, all right. So in that case, GC of S will take the form S plus 1 by T, like this one, R2 into the product R2 into C equal to T considering, and S plus 1 upon beta, R1 plus R2 like beta, and R2 into C, it's T again. And guys, we have a beta over here, 1 upon beta, all right. So the main focus is on arranging, introducing a zero and a pole. So this one, it's a attenuation factor or something like that. So generally we introduce another beta, right? That could be understood with the block diagram representation and all that. So we don't focus on this one, okay. We generally say that, yeah, after eliminating 1 upon beta, we design the lag compensator, lead compensator, or lead or lag compensator, all right. So that could be understood with the problem. For the time being, this is attenuation factor and that can be eliminated by introducing another same network over here. It's been eliminated, okay. The main focus is on introducing a zero and a pole, all right. And now the question is, which one will be of the greater value? Is this the zero greater value or the beta greater value? Guys, this is very much similar to here 1 by T divided by 1, this one, the 0, all right. And the pole 1 by T is divided by beta, and beta is always greater than 1. See, beta is this one, right? So go for random value, R1 is equal to R2 is equal to 1k, or any other stupid value, any other whatever question we have in mind. Why don't we go for another different value, 0.5, 0.6, go check it, right? In that way, beta value is always greater than 1. So it's 1.1 divided by 1. Which one? Like this will be low value and this will be the higher value. In the sense, we have for a lag compensator, we have a S is equal to, like we have a 0 at minus 1 by T, and we have a pole at S is equal to minus 1 upon beta T. And which comes first and what comes after? How to arrange this one? S plane here with the S plane with what, j omega values and j omega negative j omega, positive real values, negative real values on this side, all right. So here it's we don't have a imaginary, so it's lying on the real axis, all right. So where the pole comes, and this one, like this comes, let me say this comes over here like minus 1 upon T, and this will be the pole, all right, minus 1 upon beta T, right. This one will be lower value, yeah, that can be proved in the while we design a lag compensator, all right. So this one will be greater, it will be minus 3 and it will be minus 2, like that. Definitely this will be the position. The 0 will be lagging behind the pole. If this would have been nearer to the imaginary axis, 0 would have been dominating, right? It's all about how nearer this, which one is nearer. All right, so if this would be the position, if the reverse would be the position, it would have done something with the transfer function. All right, so 0 is lagging behind the pole, in this case electrical, like a lag network. All right, so this is the pole 0 location. It will be asked, draw the pole 0 location and explain which one is greater, etc., like that. All right, so this will be the transfer function in pole 0 form, and we had, like we had previous to this, what did we have before taking the term 1 upon t as common from here and 1 upon beta, like r2 into c, like that. What did we have? gc of s. gc of s is equal to 1 plus st, isn't it, by 1 plus s beta t, in the sense in the time constant form, j omega, what do we have? 1 plus j omega t upon 1 plus j omega beta into t. All right, so this is in the time constant form. From here we came back over here. All right, so this will be the pole 0 and this will be in the time constant form. And regarding board plot and frequency responses, we make use of this one. All right, and there are some two important equations that should be shown regarding the lag network. All right, some important derivation, a little bit, and basic information that has to be known before we go for the design part. All right, so considering this one, how to write down the phase equation for this one, phi will be equal to, for the numerator part, it's tan inverse b by a plus jb, isn't it? A plus jb, what will be the angle? Tan inverse b by a, isn't it? The similar way, b by a. So what do we have? Omega t minus, if it's in the denominator, it is minus tan inverse. Again, it is b by a, omega beta into t. This will be the expression for the phase angle of the lag compensator in time constant form. All right, so exercising on this equation, we will get some important expressions which is very much helpful in designing a lag compensator, a numerical designing a lag compensator. All right, so we need to find out the maximum value of omega at which the maximum phase angle occurs. So how to, in general, in mathematics, how to obtain the maximum value? The first derivative of the entire expression and equal to 0, the leftover part will be the maximum value. And during this process, you will have to go back to a mathematical basics. What is that? D by dx of tan inverse x will be equal to what? It's 1 upon 1 plus x square, isn't it? So we'll have to make use of this relationship over here. All right, so entire expression with respect to, like, the entire expression d phi by d omega, which will give us equal to 0, and the leftover omega, whatever omega we separate and we evaluate for omega, isn't it? That will be the maximum value of the frequency at which maximum phase lag occurs, and that omega will be equal to omega m. Let's do something. All right, so the first derivative of this one, tan inverse, now this one will be x. All right, with respect to omega, so we need to do it again. So have the simplification, the first derivative, 1 upon 1 plus omega t whole square with respect to omega. So this one will have that t again, minus once again 1 upon 1 plus omega beta t whole square with respect to omega. So we have beta into t. All right, now this entire expression being equal to 0. All right, this entire expression from here to here, this one, which is equal to 0, and this is negative this side, going that side, that will be positive. All right, so let me make use of that property, like, yeah, it's equal to 0 and it's negative. I wanted to push this to that side, that will be positive after going that side. All right, So this one. So what gets cancelled in this expression? We don't have this t, anymore, all right? And cross multiplying this one. So 1 plus omega t whole square into beta t. We don't have this t anymore, all right? So 1 into beta, that's beta plus beta omega t whole square, which is equal to cross multiplying this one, 1 plus omega t whole square beta into beta square. That could be beta into beta, isn't it, for my simplification, all right? So let this be like beta, this one it's positive, this side it will be negative, minus 1, which is equal to beta omega t whole square, and this is positive, going that side it will be negative, beta omega t whole square, all right? So beta minus 1 will be equal to, guys, beta from here, all right? Beta from here, no, beta into omega t whole square from this term, this one, and even this one. So what will be left over? It has come out, beta omega t whole square has come out. So what will be left over? Beta, and this has come out, so minus 1. So this is the reason, like for us backbenchers, we don't understand that easily. So I had to split that for my convenience. All right. Now upon beta minus 1, so we don't have this anymore, all right? We don't have this anymore, and yeah, this will be unity. We don't have this anymore, which is equal to unity, all right? So we are in search of this, one, omega, with respect to omega and omega m, all right? So omega square will be equal to 1 upon beta, this beta t square. So we are in search of omega, which is equal to 1 upon t root beta, all right? And this omega is the maximum value. Any more simplification? The first derivative, we have obtained the first derivative and equal to 0, and we have reached over here. Can we do any further simplification? Is there any simplification? No. Now this omega will be equal to omega m, all right? A very important frequency, the frequency at which the maximum lag occurs, all right? So this one. So if this is the case, we need this one, we need this value to plug in over somewhere, and yeah, let me continue over here. We had this. So guys, considering this again to obtain the expression for something, let's see what is that something. Let me have over here, all right? So guys, tan on either side, in the sense tan phi, which is equal to tan of tan inverse omega t minus tan inverse omega beta t, all right? So that one, and it's a tan a, this one, tan a, entirely tan a minus tan a minus b, all right? This entire one b, and so that will give us tan a minus tan b. What is that? Tan a minus tan b by 1 plus tan a tan b, isn't it? What is that? Let me write it over here. Tan a minus b, what will be? Tan a minus tan b by 1 plus tan a tan b, all right? A small simplification here itself, all right? Tan, we have that tan, and what is a? This one, this entire tan inverse omega t is a, and tan inverse omega beta t is b, all right? So tan a, so what is that? Tan inverse a is tan inverse omega t, all right? So this tan and tan inverse will be cancelled, tan and its inverse, that will be cancelled, and so we'll be left with only omega t when we write this entire expression as this one. So no more tan over here, okay? So no more tan. So tan a right? In that A we have tan and tan inverse. Tan and its inverse gets cancelled, and omega t will be left over from A. What about tan B? Tan B, this tan and tan inverse gets cancelled, it will be omega B t upon 1 plus omega t omega B t, beta into t. Alright, so which is equal to, guys, any simplification over here? Yeah, omega t is common from both the terms. Omega t is common, 1 minus beta. Omega t, yeah, 1 over here and omega t beta over there, upon what? 1 plus beta omega t whole square. All right, hope you understood the simplification. And this is from this one. Okay, we made use of that transition over here. All right, and any more for the simplification? Of course, we have yeah, omega t whole square here from here. What did we have? Omega equal to omega t equal to, right, omega t equal to 1 upon root beta. All right, so omega t whole square will be equal to 1 by beta. All right, the same omega t square over here. So this one we will have this one as and in the numerator 1 minus beta. All right, 1 minus beta, and omega t is this. All right, so in the numerator 1 upon root beta we have, and this one as it is plus beta also as it is, and this omega t square is 1 by beta into multiplication, isn't it? So what gets cancelled over here? We don't have this beta anymore, so the simplification will be yeah, tan, what are we evaluating for? Tan phi is equal to what is that? 1 minus beta by this shifts down root beta into 1 plus 1, this we don't have this anymore, to root beta, isn't it? And this one, this tan phi is obtained making use of this expression, isn't it? This one we may be have rewritten over there, we have plugged in over here. So this is omega m is plugged in, right? We made use of omega m. All right, so it's all about omega m. Now this one will be phi m, or else simply phi m will be equal to tan inverse on either side. So tan inverse 1 minus beta by 2 root beta. Even this will be asked. Derive the expression for the phase angle, the maximum phase angle of a lag compensator. All right, so we have to remember this one. All right, so even this is important, and this expression, and this expression should be in sine terms. All right, so to do that we need to have that expression in terms of sine. So how to do that? If we have a tan, we can go for a triangle. If you have a tan, what is tan? Opposite by adjacent in a right angle triangle, isn't it? Construct a right angle triangle, let that phi m be here. All right, from this one. So what will be tan phi m? Opposite by adjacent, isn't it, to that? So what did we have? Here? It's a 1 minus beta by 2 root beta, isn't it? So opposite by adjacent, 1 minus beta and 2 root beta. What comes over here? Pythagoras theorem, which you have in the very basics of 10th standard and all, isn't it? From the previous grades we make use of that one. This square equal to this square plus this square, isn't it? So what is that? Is equal to 2 beta whole square root, all right, plus 1 minus beta whole square. So what will be this? It's a 4 beta plus a minus b whole square. All right, so a minus b whole square, a square plus b square minus 2 A, B. Alright, so what do we have here? Plus 4 beta minus 4 beta. We have 1 plus 1 square plus beta square. What? 1 square plus beta square plus 4b minus 4 beta minus 2 beta plus 2 beta into 1. So what do you understand? Into 1, a square plus b square plus 2ab. So how can we close this one? 1 plus beta whole square, which is equal to this square. All right, so this, I'm sorry, from the beginning, this square, this will be equal to like root on either side gets cancelled, and 1 plus beta. So we have, this is 1 plus beta. All right, so which gives us sine over here. Make you concentrate over here. Sine phi m will be equal to what? 1 minus beta by 1 plus beta, or else phi m will be equal to sine inverse 1 minus beta by 1 plus beta. Now the important expression which is used in designing a lag compensator. Thanks for watching.